This is Fan Jiang from Xilinx 7nm Technical Marketing. Today, I would like to introduce how to accelerate deep learning models on Xilinx 7nm Versal card. Here is the agenda for this session. At the very beginning, I will briefly introduce the VCK5000 card, which is the Xilinx 7nm Versal card, and jump to the 3 overlays for different deep learning tasks afterwards. The introduction includes a quick demo on how to run a Vitis-AI sample on this Versal card, with a summary at the end of this session.
VCK5000 is the PCIe card targets on data center acceleration development. You can find the hardware features on the bottom left table. The core chip is Versal VC902 -2M grade. It has 16 GB DDR4 memory support, while the power consumption at max TDP is about 300 watts. Currently, the card is still in EA stage, so there is no Vivado or Xilinx BSP support. The card with production silicon will shipping from Q3 2021. As it's in EA stage, the relevant docs or files have been put on a separate launch as shown on this page, where the users need to register for access and download. From May the 6th, Xilinx kicked off an exclusive offer for this card at only $24.95 US. Users who have interest or want more detailed info could contact us through the email on this page. At this release, we have provided 3 different overlays, one from CNN, one for the MLPerf reproduce, and one for the BERT model. One question I have been asked frequently is why Xilinx need to deliver separate IPs, and is it possible to deliver one single IP which is uniformly applicable to all AI-related tasks? Before I answer this question, let's see what's the difference between CNN models and BERT. The largest differentiation is their input format. The input of a CNN could be a group of images or a fraction of video clips. So each frame of the input is independent, while any exchange or disorder makes no difference to the output. So users could easily use large byte size or similar methodology to do the computation in parallel to achieve the acceleration. While the input of the BERT or other NLP models will usually be a short period of speech or signal, and any exchange or even latency would cause the error during inference. So back to the question, it is possible to design one IP like CPU, which works for all AI applications, but it's impossible to have one IP works for all AI applications with high efficiency. Adaptable hardware overlays are the optimized solutions to adapt to more and more AI tasks with same chipset. The DPU overlays on VCK5000 for CNN tasks is called DPU-V4E. On the right is the microarchitecture of the DPU-V4E. We have put the COMPs on the AIE cores and leave the rest engines on the PL side. On the left is the resource utilization. So each COMPE have 48 AIE cores, which provides 7.7 tera operations inter-8 computing ability. The table shows the resource utilized with 8 PEs enabled, which is the maximum we could put it in. The design takes almost all the RAM resources to reduce the DDR read and write as much as possible. The DPU-V4E is also an instruction-based engine like GPU-v2 or GPU-v3e, so the compiler efficiency is very important when considering the end-to-end performance. I would like to highlight two compiler features here. The first one is the VCK5000, which takes the full use of on-chip memory to store the weights info and prevent the data movement from and to DDR. The second one is image bonding. It only works for the models like ResNet, which has a series of 7x7 kernels lined up one after another. As the size of the memory for feature map is 8x16, which means we could actually put two images in and compute simultaneously, it's more like a batch 2 compiler. So why only 7x7? Theoretically, we could also put like 3 5x5 kernels, right? The first reason is technical difficulty. It's pure instruction or compiler works, so it would be very difficult for the compiler to identify a model, so which part is for normal instruction generation and which part is for the image bonding acceleration, and with different kernel size. The scheduling work would be way more complicated than today. The second reason is the image bonding. Well, beneficial only the data movement time is far less than the computational time. So batch 3 5x5 kernels means you need to spend time to load 2 extra kernels to make them computing together. You could still expect some improvements, but not that significant. I didn't do a serious count, but the concept is, at the kernel size shrink, you could load more kernels in to do multi-batch compilation, but it takes more time to load the data as well. I don't know if you have used the Vitis-AI tools before. The Vitis-AI understood as the unified AI inference solution stack, as it contains not only a toolkit, but a full stack from model zoo to computation engine. And the word unified here could be explained from two perspectives. The first one is the unification of user applications. The input could come from automotive LiDAR, or surveillance cameras, or from medical sensors. So as long as the model has been trained with the framework we have supported, it could rely on the Vitis-AI tools to compile to the Xilinx representation, which is called XR in short. And the second one is the unification of the platforms. The DPU could be integrated on different hardware across edge to cloud, and also from 16nm to 7nm, with no extra overhead. The VRT here stands for the Vitis-AI runtime, which has been developed based on the XRT. In Vitis-AI 1.2 and the previous version, there are only 6 APIs in the render class for coding across edge and cloud. So with those APIs, you may not get the optimized end-to-end performance, but it won't cost you extra overheads when changing the platform. In the new release, we have added a few more APIs to achieve the zero copy features. So previously, if you have 2 HS kernels running sequentially, the output of the first kernel will be write to the DDR and wait for the read from the second one. So zero copy will allow the output of the kernel 1 to store in on-chip memory and pass the pointer to kernel 2 directly. So it could save the time for one read and write with DDR. Vitis-AI library provides high-level C++ or Python API based on libraries and mainly focuses on 3 aspects: the ease of use and optimization, and open source. For ease of use, AI library provides reference codes of pre and post processing for all the models in the model zoo. So users could easily reproduce the benchmark listed on our GitHub page and AI library has done some optimization at the coding phrase to avoid the unnecessary cost at pre and post processing. All the codes stated just now are fully open sourced, so users could use it directly or take it as a reference to do your own design. The hardware-aware pruning means coarse pruning, not fine-grained. You could achieve like 23% hardware performance improvement with 26% cutoff. So if you remember the similar model on DPUV2, we could prune the models to 50%, 30%, or even 10% of original size, but only 74% here on DPUV4E. It is because the AIE can't deal with irregular channels. For example, if the parallelism is 128, it means there's no difference whether the channels are 129 or 356. They both take 2 clock cycles. So the pruning will not be a high priority directions for Versal optimization. And MLPerf results, so I will talk about it later. The device power. Device power matters, especially for the edge use case. Xilinx may not have advantage at computing ability, but will take the lead at computing ability per watt. These are the models we could support today from Xilinx Model Zoo. The Model Zoo provides stiff earth models that have been well trained with public datasets. Users could easily reproduce the result or take it as a baseline to retrain the model with some private dataset. All the training scripts along with superparameters are provided as well, which avoid the users to do the job from scratch. Now in the Vitis-AI 1.3.1, we have 92 models altogether from Caffe, Pytorch, TensorFlow, and TensorFlow 2 within the Model Zoo, and 52 of them are supported with VCK5000. The rest will be supported in the upcoming Vitis-AI 1.4 release. Here is a fraction of the list for the benchmarks of the models we have supported in Model Zoo. I won't go through it one by one, so people who have interest could find the full list with the link at the bottom. Here is the MLPerf result. MLPerf is one authoritative benchmark baseline admitted by many institutes and companies. The benchmark here is compared to NVIDIA T4 with 3 different models. On the left is ResNet 50. The bar graph shows the hardware performance on different configurations. 6433 is the number of our submission performance. It's running at 1.33 GHz AI frequency with a customized platform, which has lower URAM utilization. The 5064 is the number on the standard release platform with 1.2 GHz AI frequency without any optimization, while the 7019 is performance with 1.5 GHz AI frequency running with full force. And the end-to-end performance is 5921 frames per second on the server mode and 6257 frames per second offline. In the middle is the ULV3 and SSD ResNet 34 on the right. Why we choose these 3 models? The first reason is they are all MLPerf assigned models, and it will be better and easier for us to do an apple-to-apple comparison to NVIDIA curves. The second reason is the input size and model complexity are increasing from left to right. ResNet 50, the input size is 224 by 224, which has 8.1 giga operations. while the UV3 is 416 by 416 has 66 giga operations, and SSD rests 34. It is 1200 by 1200, which is 433 giga operations. So you can see from the graph here that we could be T4 when the model is small or medium, and T4 has an advantage on large model computation. Okay, BERT. The BERT stands for the bidirectional encoder representations from transformer. It's the hottest and state-of-the-art language model in natural language processing, NLP in short. And transformer is a very popular structure, like the convolution in CNN models. It's powerful not only in NLP, but people start to look at the possibility to integrate the transformer in image processing, or like classification or detection or super resolution. So this is the first demo with Versal devices. Xilinx did not do any retrain or optimization on it. We just used the model pre-trained by Google with score dataset, quantized it, and deployed on VCK5000. The BERT IP has utilized 384 AI cores for dense computing operations like GEM or layer normalization. GEM stands for the general matrix multiplication. The other light-weighted operations like embedding, load or store are on the PL side. So altogether, the BERT IP has supported the majority of mainstream BERT operators. To be noted that the BERT IP is not an instruction-based IP, but templates-driven. All the computing engines are implemented with the AIE across. The BERT compiler will read the model configurations and translate it to the AIE and RTL codes based on the templates. So any retrain or even any very tiny reconfigurations of the model needs to regenerate the axial bin. The progress of the regeneration is not that complicated, but we haven't opened it up for external users to do that at the moment. So it is only a demo at this EA stage. The BERT overlay has unified runtime engine, just like the DPU for DDR-based audio cards like U200 or U250. And some highlight runtime features are reserved and works for the BERT as well. For example, this multitask pipeline, it would allow the embedding 1 running on the PL side while the BERT 0 running on the AI engines. So it improves the end-to-end performance and reduce latency. The quantization is quite different compared to the CNN overlays. In CNN, we only suppose 8-bit computation, and we believe it will be sufficient to maintain the accuracy. If not, we could have other tricks like quantized aware training to bring the accuracy back. Similar approach doesn't work for BERT, so tiny weight bitwise change will lead to an unbearable accuracy loss. So we are using a mixed precision here, where most of the layers are computing with integer 8, and reserve some very sensitive layers at float point 32. This is a timing breakdown analysis of the layers within transformer structure. You can see from the table on the right-hand side that the FFN layer takes nearly 60% of the overall computational time. The FFN is more like the fully connected layer in CNN models, which is not only occupies the computing engines but also the transmission bandwidth. So the future work of the BERT overlays will focus on the FFN optimization. This is a summary of the current BERT demo released in Vitis-AI 1.3.1. The F1 benchmark on scored 1.1 is 86.5%, while the scored stands for the standard question and answer dataset, which is a public dataset for BERT model. The throughput is about 742 sentences per second with 9.2 millisecond latency. Right, as a summary, please visit and register to our VCK5000 launch for the 3 different DPU overlays. The DPU V4E is the CNN solution targeted on cloud-side applications. And Xilinx has provided the first version of BERT demo on VCK5000, but still in EA stage as a demo. And what's more, there is another package for users to reproduce the MLPerf result. Right, so that's everything for the presentation, and I will show you a quick demo how to run Vitis-AI samples on VCK5000. Right, so before we start this demo, if you are using a brand new VCK5000 card, please visit this Xilinx VCK5000 launch and simply click this Vitis-AI for VCK5000 tab and follow the instructions here to download and install some prerequisite packages. So most important things you need to install is the XRT in the platforms. So we have packages listed here based on different operating systems. You can just download and install them accordingly based on your operating system. Okay. So if you're using a brand new VCK5000 card, the first step, you could use this lcpsi command to see if your cards boot up successfully. And then the first step will be install the XRT using this command. So make sure you have the sudo authority to do so. The second step will be extract the turbo file for VCK5000 platforms. So when you extract this turbo, you will have 3 platforms listed here. So the step 3, you need to install them. So this platforms has some dependencies in the middle, so please make sure you have installed them in the order as shown here. Okay. For Xilinx card is allow the users to install multiple platforms on it, but only one of them could actually running on it. So the step 4 is to program the platform on VCK5000 card. So step 5, make sure you do a code reboot after this flash operations. So this is the compulsory step for each time you program a new platform on Xilinx of your cards. Step 6 is to install the XButler. This is the link for you to download the XButler. So make sure you have installed the version 3.0.2. If you download and install another version, there could be some unexpected errors due to the version mismatch. Step 7 will be download the Excel bins. So there are 2 versions, one for 6P and for 8XP. For the 6Ps, there could be some performance gap compared to 8P, so you can choose either of them. Step 8 will be download this VCK5000 model packages. There are some pre-built models for you to download it here. If you are using your own models, or if you're using some float point models, you can also follow the Vitis-AI standard workflow to do the quantization compilation is supported. For this demo, we just use this pre-built model to show you the workflow. Okay, so let's start the demo. So here, I have already got the XRT, the platforms, the XButler, and everything installed already. And let's have a look what we have in this folder. This Docker run script is compulsory for you to start the Docker container. These are the two Excel bins I've downloaded from the lodge, and this is the images downloaded to do the inference, and this is the pre-built models downloaded from the lodge. Okay, so and before we start, we could just have a quick look for the current versions of XRT and platforms we have installed. We could do first to do Xilinx XRT bin xpm flash scan. Okay. Okay, here you can see this is the platform version we have installed and running currently. For XRT, we could similar to PD Xilinx XRT bin xpm scan. Okay, and 2.9.3.17. So this is the current XRT versions we have used. And we could simply check the XButler sudo service XButler status. So our XButler is currently running without any issues. Okay. So now we can just copy our Excel bins to the assigned directory. We could do copy A4E, where we use this 8PE. To PD Linux overlay. Okay. To see if the Excel bins installed correctly, we could use xbuild commands to check. We could do xbuild program. -P is to assign the Excel bins, which we have copied to this directory. Okay, and -D is the destination. You need to assign cards, because for this server we have 3 cards running on it, and the VCK5000 is the number 1, so we use -D1 to assign to that. Okay, executed program succeeded, so everything is running fine. So we can enter the Docker now. Before enter the Docker, we do another Docker pull to make sure we're using the latest version, Linux Vitis-AI CPU latest. Okay, it's the latest version, and we could use this docker run command to start the Docker container. So for this server, we don't have a GPU card installed on it, so we'll use this CPU Docker. If you have a GPU on it, you could use the GPU Docker, so they both fine. Right, so 1.3.598 is the latest version of Docker, so make sure you're using the same version as I have here. And when we enter Docker, we need to cite some environment variables first. Export. Firmware equals the Excel bin we have used. Right. And another one to enable the softmax. Okay. A directory for the precompiled models, we will use this make directory. User share Vitis-AI models. We'll create a new folder here. And so this is the models we have downloaded. So we just simply copy everything within it to the directory I created just now. Copy. Alright. So I've already got the images here, and we need to extract the images to the sample folder as well. We do okay, then we could enter the sample folder. Here are the samples, what we have here. We could choose any one of them. So I will use this face detect as example. So that's the face detect. So in each sample folder, we will have a README files here. We could simply follow the instructions here to start the demo. Let's just do cat readme. So the first step, you need to compile the samples, and then just simply run with the command like this. Okay, so we just to do build. Right, and we just run the examples. Use this command. So this is a command to run inference with a single frame. So the output should be something like this. Okay, so this is face detect. So actually you will have, this is the confidence, but it's a face, it's a human face. And this is the coordinates of that face detected. This is another one. So basically, there should be 2 human faces within this frame. This is face detect. Oh, and okay. We could also try this test performance. So to test the performance, we could use this test performance face detect, and then choose the model which is dense box. 320 is the size of the input frame, and then this is the list we use to test. -T is the number of threads we're using, and -S is the number of seconds we're running. Oh, I forgot to set this thread. Right. Okay, finished. So this is the frame per second, and this is the end-to-end time we have used, and this is the pure hardware time we've used. Right? Okay, so let me quickly run another models. Let's say Universe 3. Okay, similarly, we could follow the README files here. Okay, so that's what we got. The Universe 3 is the detection model. So what we will have is first is the classification, so which category it belongs to, and then the coordinates of this detected objects, and then the confidence. So what's the probability, how confident it is to be detected objects. Okay, so that's everything for the VCK5000 demo. Thank you for watching.
Welcome back. So thank you for joining me with this quick demo. As a close mark, for any inquiries or questions, please kindly send us email or leave your comments on the Xilinx forum. So that's everything for this session. I will see you again in the next webinar. So see you. Bye.